Everybody. Uh, Today's session, as you see, I titled Seismic Design Considerations Beyond the Basics. I that is the most descriptive title that I could come up with for what I have in mind to discuss today. These are the topics. First of all, drift, P delta effects, building separation. Drift, we have discussed to quite a significant extent. The other things we have not. Redundancy, rigid versus flexible diaphragms, basics of structural diaphragms, and diaphragm seismic design force level. Now, most of these topics are largely not covered by the BNBC. That is a bit of a surprise because many of these topics, as you will see, are quite important. However, they are most of the time mentioned in the BNBC, not covered by mentioned. And that's what I will start with. So in BNBC 2020, you have section 2.5.2, earthquake resistant design basic concepts. And I quoted from that section on an earlier occasion, talked about buildings being symmetrical and so forth. Now on structural redundancy, this is what BNBC has to say. A high degree of redundancy. Redundancy to me is multiple load paths, as I think I said in passing earlier. More than one way for the loads to travel from the point of application down to the ground where all loads ultimately belong. That's what redundancy basically is. So BNBC says a high degree of redundancy accompanied by redistribution capacity through ductility is desirable. For me, this redistribution through ductility is different from redundancy. And maybe to conserve time, I am tempted, but I will not go there. Enabling a more widely spread energy dissipation across the entire structure and an increased total dissipated energy. The use of evenly distributed structural elements increases redundancy. Structural systems of higher static indeterminacy may result in higher response reduction factor R. This concept is also not there in the code. We do not take an increase in R when we have a redundant or a highly redundant structure. Okay, but this is the entirety of what BNBC says. I will show you ASCE 7 provisions, which are full-blown provisions that we remember. The redundancy factor rho is in the designed load combinations. Earthquake effect E is rho times horizontal earthquake effect plus vertical earthquake effect. And E is combined with the effects of gravity loads through the designed load combinations. Okay, that's how the redundancy factor comes into design. The next item, this is also from section 2.5.2 of BNBC, horizontal bidirectional resistance and stiffness. So horizontal earthquake motion is a bidirectional phenomenon, and thus the building structure needs to resist horizontal action in any direction. I actually discussed that with you under orthogonal load effects. Remember, I don't remember whether it was the last time or the time before, but orthogonal load effects take care of exactly what BNBC is talking about here. The provisions are not in BNBC, but I give them to you. The structural elements of lateral force resisting system should be arranged in an orthogonal pattern, ensuring similar resistance and stiffness characteristics in both main directions. That is not always up to the engineer. The architecture of the building will dictate much of this. The stiffness characteristics of the structure should also limit the development of excessive displacements that might lead to either instabilities due to second-order effects or excessive damage. Okay, so this is what BNBC says under horizontal bidirectional resistance and stiffness and orthogonal effects. Provisions of ASC 7 I have discussed with you that goes far beyond this kind of stating principles kind of idea. The next item, torsional resistance and stiffness. Besides lateral resistance and stiffness, building structures should possess adequate torsional resistance and stiffness in order to limit the development of torsional motions, which tend to stress the different structural elements in a non-uniform way. In this respect, arrangements in which the main elements resisting the seismic action are distributed close to the periphery of the building present clear advantages. Okay, all of that is true. From a torsional point of view, you are much better off if the resisting elements are along the periphery. That again is not always possible, but that definitely is desirable. But then, you know, these are this kind of statements are not enforceable. There are no provisions here. Okay, this is advice. Diaphragm behavior. I have 2 slides, and that's all BNBC has to say on this huge topic. In buildings, floors, including the roof, act as horizontal diaphragms that collect and transmit the inertia forces to the vertical structural systems and ensure that those systems act together in resisting the horizontal seismic action. Okay, we will discuss this at length. You will see what this is talking about. Anyway, this is very basic. Floor systems and the roof should be provided with in-plane stiffness and resistance and with effective connection to the vertical structural system. Particular care should be taken in cases of non-compact. That means, you know, one side is very large compared to the other. In cases of non-compact or very elongated in-plan shapes, and in cases of large floor openings, especially if the latter are located in the vicinity of the main vertical structural elements, thus hindering such effective connection between the vertical and horizontal structure. The in-plane stiffness of the floors shall be sufficiently large in comparison with the lateral stiffness of the vertical structural elements, so that the deformation of the floor shall have a small effect on the distribution of the forces among the vertical structural elements. Okay. The first part, where it talks about openings and so forth, is very basic, good sense, although there is no provision here. The last part tends to suggest that all diaphragms should be rigid, that they should not deflect much in their own plane. That is really not a necessity. Uh, and so this is where this diaphragm stiffness discussion comes in, flexible versus rigid diaphragms. We will talk quite a bit about it. And to a large extent, we will talk about not all of it, but at least the diaphragm design force level. I will talk about. Okay, so that brings us to the first set of topics: drift, P delta effects, building separation. Everything in today's presentation is AC7 material as adopted by the IBC. I mentioned previously that the seismic design provisions of BNBC 2020 are those of ACE 705. Excuse me. And that's where I typically have gone uh, in the, excuse me, of the topics that we are on to. Building separation provisions changed rather significantly from AC 705 to AC 710. AC 705 really did not have specific building separation provisions. It was kind of in principle sort of provision like in BNBC. AC 710 has specific building separation provisions, which I think are important. So in this segment, I have gone to AC 710 definitely for the building separation part. The rest of it is AC 705 or AC 710. There is really no difference between the two. Some slides have AC 710 in the title, some have AC 705, but again, other than building separation, there is no difference between the two. Okay, the lowercase delta sub 3 E is the elastically computed displacement at floor level 3, okay, under the code prescribed seismic forces. So you take the design base shear, you distribute it along the height of the structure in the manner prescribed by the code. That gives you lateral forces at the various floor levels, which we denote by capital F sub X. We do an elastic analysis of the structure under those distributed forces. The displacement coming out of that analysis for floor level 3 is delta sub 3E for elastic, and at floor level 2, it is delta sub 2E. E again is for elastic, 2 is for floor level 2. Okay. The difference between the two, this capital delta sub 3E, is the interstory drift for story 3. Okay, this is level 1, this is level 2, this is level 3, this is story 1, this is story 2, this is story 3. So story 3 is the story below level 3. Okay. The capital delta sub 3E is interstory drift in story 3, and it is elastic interstory drift. Okay. If we divide this delta sub 3E by the story height of the third story, H3, that is called interstory drift ratio. Now I have I think at least in passing, discuss this with you. Delta sub E is typically determined at the center of mass of each floor level. When torsion is not pronounced, that's what we do. Delta sub E is determined at the center of mass of each floor level. When centers of mass of two consecutive floors do not align, so the capital delta sub 3E would be the deflection at the center of mass of level 3 minus the deflection at the center of mass of level 2. However, if the centers of mass of level 3 and level 2 are not vertically aligned, then the interstory drift would be the deflection at the center of mass of level 3 minus the deflection at a vertically aligned point below the center of mass of level 3 on level 2. Okay, so when centers of mass of two consecutive floors do not align vertically, story drift is to be determined based on the location of the center of mass of the upper level. You go with the center of mass of the upper level and a point vertically below the center of that center of mass on the level below. For design category C through F structures with torsional irregularities type 1A or 1B, the drift must be checked not at the center of mass or center of mass and a vertically aligned point below, but at vertically aligned points along the edges of the structure, as I discussed with you earlier. Okay, torsion will mean that the deflections are larger along the periphery than at the center of mass. So we go with vertically aligned points along the edges of the structure. Now, theoretically, you have to go around the periphery of the building, but with a little bit of experience, you kind of know where to take these vertically aligned points. This last issue I discussed with you already. Now, a variation of this picture I have shown you many times. The load deflection curve of a particular structure subjected to the design earthquake of BNBC 2020. If the response were elastic, the total force developed in the structure would be capital V sub E, and the total displacement not shown here, we called it lowercase delta sub capital E on an earlier occasion. Anyway, today the important thing is that we are designing for V sub E divided by R. That's our design base shear. And we analyze our structure elastically under that shear distributed according to the height of the structure in the manner prescribed by the code. The corresponding displacements at the various floor levels are delta sub E, okay, as we just saw and discussed. Now, as mentioned previously, delta sub E would be much smaller than the displacements the structure will actually see if the design earthquake were to hit, because delta sub E is being calculated under the reduced displacement, reduced forces V sub E over R. Okay, I mentioned previously that the deflection corresponding to elastic behavior does not change much when behavior is inelastic. When you make your structure less strong, part of the deflection is elastic, part of the deflection is inelastic. The total deflection does not change much from when the structure behaves elastically to the design earthquake. Okay, so this deflection is not a whole lot different from the deflection corresponding to V sub E. There are proposals that we make them the same, but so far we have not made them the same, except here and there. Anyway, we estimate the actual design earthquake displacements by multiplying the calculated delta sub E values by the displacement amplification factor C sub D, which is given to us in the R values table. Okay, all of that I have discussed at length with you. None of this should be anything new. Okay, the C sub D values, as I said, are given in the R values table, table 12.2-1 of ASC 710. That is, the corresponding table is in BNBC also, and on other slides, I've given you the BNBC table numbers. Okay. Now, so lowercase delta sub XE, capital delta sub XE, capital delta sub XC divided by H sub X. We have discussed all of that. Now, also discussed earlier, when we do our drift check, when we check that the interstory drift is interstory drift delta, including C sub D, is within tolerable limits as given in AC7, we multiply the design deflection by the importance factor I. Okay, so we start with delta, lowercase delta sub 3e elastically computed. We multiply that by C sub D to get to design earthquake displacement, and then we divide by the importance factor, because the drift limit against which we check the interstory drift is a function of the importance of the structure. The drift limit for a hospital is half that of an office building on the same site. For an office building, the interstory drift we allow is 2% of story height. For a hospital, the interstory drift we allow is only 1% of story height. And so the idea is that we should not penalize the same building twice. First, by instituting a tighter drift limit, and second time, by calculating larger deflections for an important building, because the force under which we are calculating the displacement, the lateral force, is augmented by an importance factor I. So we take the I out of the deflection calculation. So this quantity, C sub D times delta sub XC for floor level X divided by I, that quantity at the top of a story minus the same quantity at the bottom of the same story. If our story is the third story, that would be delta sub 3E minus delta sub 2E divided by I, is the delta sub 3 that we check against the drift limit. Okay, I think you will find these slides very, very clearly made. So I spent time on this on a previous occasion, so I think that should be sufficient. The the interstory drift delta must be within tolerable limits. Now, something important that I did not mention in the past is, or maybe two things. Okay, so remember, in the design base shear equation, irrespective of seismic design category, the design base shear may not be any less than 0.44 S sub ds times S sub ds times I times W. or the design base shear coefficient cannot be any less than 0.44 S sub ds times I. And under no circumstances can it be below 1%. When S sub ds is low and this, this number goes below 1%, we keep the design base shear no less than 1% of building height. Now that limitation need not apply in drift computation. Okay, you can let the design base shear go as low as the 1 over t or 1 over t squared equation would give you. The other limitation that need not apply, need not means exactly what it says. You do not have to apply it, but if you apply it, that is okay with the code. When we talked about period computation, we start with approximate period T sub A, which is given by formulas in the code. Then we compute period rationally by any procedure that is in conformance with the principles of mechanics. The rationally computed period T depends on the stiffness assumption that we make in the period computation. And because of that, T is limited to being no more than a multiplier times the approximate period. The multiplier in Bangladesh is 1.4. So we are never allowed to take the rationally computed period any larger than 140% of the approximate period. But that is for force calculations only. For deflection calculations, that limit need not apply. So those two need not apply items you have to be aware of, very definitely aware of. Okay. Now, P delta effects are things that you are familiar with. Under lateral loads only, this would be the interstory drift. When you consider the gravity sitting on the frame, that interstory drift increases to from delta sub 0 to delta sub f as shown in the picture. In dealing with P delta effects, we define a stability coefficient, which is basically the secondary to primary moment ratio. V sub x is the story shear, that multiplied by story height is the primary moment. P sub x is the unfactored gravity load at the level where we are doing this calculation. Okay, total vertical design load factor of 1 at story above level x. Delta, you know, is the computed design level story drift, including C sub D. In P delta calculations, we have historically taken elastic drift, not the drift including C sub D. So we take the C sub D out, we divide by C sub D. And then in recent times, we have included the I factor in this expression, meaning we would like to calculate a larger stability coefficient for more important buildings, because that stability coefficient, again, we like to keep within limits that we believe will not cause instability of the structure. We want to play it safer for more important buildings. So the stability coefficient theta is given by this formula. If theta is less than 0.1, 10%, then P delta effects can be neglected. These days, P delta effects are taken into account by the computer program that we use for structural analysis. So there isn't a lot of incentive for ignoring the P delta effects, you might as well keep the option on to consider P delta. But if you want to neglect it, this is allowed by ASC 7 if the stability coefficient is less than 10%. If the stability coefficient exceeds 10%, then the largest value of theta along the height of the building, okay, shall not exceed, or yeah, theta. So you go along the height of the building, the largest value of theta shall not exceed the 0.5 divided by beta times C sub D. C sub D we're familiar with. Beta is the ratio of the shear demand to the shear capacity of the story in question. Shear demand to shear capacity. Shear capacity. So story in question, the shear capacity will be supplied by the columns and the shear walls. So if you add up the shear strengths of the columns and the shear walls, that is your story shear capacity. The shear demand will again have to come from analysis. Now that ratio is not the easiest number to calculate, so you can conservatively take it equal to 1.0. That is allowed by ASC 7 specifically. So theta, in other words, shall not exceed 0.5 divided by C sub D. Okay, if C sub D is 5, you get the same 10%. Under no circumstances, irrespective of what your beta may be, C sub D may be, the ratio cannot exceed 1/4. Secondary moment cannot be any more than 1/4 of the primary moment, because then we are pretty afraid of structural instability. So if that happens, theta goes beyond or becomes equal to 1/4, then you will have to change something in the structure to make it more stable. When theta is between the two limits, 10% and theta maximum, as given on the previous slide, one simple way of accounting for P delta effects is multiply all computed element forces and displacements by 1/1 minus theta. Okay, this we have done for a long time, works pretty well, although these days, as I said, the computations will be done on the computer, and we probably will not do this. But this has been very popular over the years. So multiply all computed element forces and displacements by 1/1 minus theta. Check drift limits using amplified drift and design for amplified forces. Okay, the note that started at the bottom of the previous page, and you can delete because that note is repeated here. So P delta effects may also be automatically included in the structural analysis, as I have been saying. However, the theta max limit still applies even when you include P delta in your analysis. The theta max limit still applies. The value of theta computed using the results of P delta analysis is permitted to be divided by 1 plus theta before checking against the theta max limit. So when you get your drifts from an analysis including P delta effects already, the deflections that you get from the computer can be divided by 1 plus theta, because the check should be you see the deflection, the drifts that you check against the limit should be drifts in which P delta is not included. If you take the drifts from an analysis where P delta is already included, you need to take the P delta consideration out, and that's where the division by 1 plus theta comes in. Okay, so read this carefully. I think you will see exactly what AC7 has in mind. Okay. The drift limits are in table 12.12-1. I showed it to you earlier. I don't know that I need to spend more time on this. Most of the time, as I pointed out, you'll be under all other structures, this last row. And your drift limit is 2% of story height for risk category 1 or 2. Actually, this is called occupancy category in the older documents like your code. 1.5% of story height for category 3 buildings, which are assembly buildings. A lot of people congregate in one space at one time, and the limit is 1% of story height for essential facilities and hazardous facilities. Okay. Something that I did not mention is in this box. For seismic force resisting systems comprised solely of moment frames in structures assigned to design category D, E, or F, the design story drift delta shall not exceed delta sub A divided by rho, the redundancy factor for any story. So this is a major penalty for structures that employ moment resisting frames as the seismic force resisting system, no shear walls. Okay. So again, for seismic force resisting systems comprised solely of moment frames in structures assigned to design category D, E, or F, the design story drift delta shall not exceed delta sub A over rho. In other words, you are tightening the drift limit. If rho is 1.3, your drift limit is way tighter. Okay, so this is something I need to point out because many people I know just miss this provision in AC 710. It was put there for a reason, and you need to understand it and apply it. Okay, that brings us to structural separation to avoid pounding or hammering, as it is called. I think this picture is pretty graphic. If we want to prevent hammering, then that separation distance has to be sufficient. Okay. This is a picture taken after the 1994 Northridge earthquake, and you see the damage due to hammering that has happened. Now, this is the structural separation provision of AC 710. Here, I mentioned AC 710 is quite different from AC 705. All portions of structure shall be designed and constructed to act as an integral unit in resisting seismic forces. That definitely is one choice. No gap, no nothing. You tie everything together. All portions of structure shall be designed and constructed to act as an integral unit in resisting seismic forces, unless separated structurally by a distance sufficient to avoid damaging contact as set forth in this section. So you will tie the whole structure together, or you shall separate portions of your structure by gaps that are sufficient to avoid what AC7 has chosen to call damaging contact. Okay. So to avoid damaging contact, the the separation distance between two structures, adjacent structures on same property, shall be separated by at least delta sub mt, and delta sub mt is the square root of the sum of the squares of these two quantities. Delta sub m1 and delta sub m2 are maximum inelastic response displacements, as they're called, of adjacent structures at their adjacent edges. Okay, so these are maximum inelastic response displacements. I'll define that in a second, of adjacent structures at their adjacent edges. These are not deflections at the centers of mass. Okay. Now, let's take an example. Let's say there is a shorter structure and a taller structure. The roof level deflection, this inelastic response displacement, which I have not defined yet, let us say this delta sub capital M at the roof level of the shorter building is 75 millimeters, and the inelastic response displacement at the same level of the adjoining structure. This is not at the roof level, but at the, here you have to take, so roof level of the shorter building and the same level of the taller building. Let us say that deflection is 100 millimeters. Roof deflection will be significantly higher than that. Okay. So the separation distance between the two buildings has to be square root of 75 squared plus 100 squares, and that comes to 125 millimeters. Okay. Now, if we wanted no contact between the two buildings, no contact whatsoever, then we would have to separate them by a distance equal to 75 millimeters plus the roof level displacement of the taller building, which would be, let us say, 150 millimeters. So the gap would be 225 millimeters. This gap, in ASC7's opinion, is sufficient to avoid damaging contact. There will be contact, but that would not result in significant damage to the structures. Okay, I think I have shown you this picture from Mexico earthquake 1985, and the point of the picture, and this is always true in this business of hammering, the most important thing is whether the floor levels of the neighboring buildings align or they don't. In this picture, they are not aligned. So the heavy floors of the right building hit against not quite mid-height, but along the height of the column of the next building, and a few poundings like that, the column gets damaged, and then a whole portion of the building can come down. Okay, if the floors are aligned, the damage is significantly less, but we cannot regulate by building code that floor levels of neighboring buildings shall be aligned. That is pretty absurd. So this is why we go to this avoiding damaging contact. Okay. Now, maximum inelastic response displacement, delta sub M, what is it? It is a delta maximum multiplied by C sub D divided by I. This is very similar to the delta sub X that we use in drift check. That was delta sub XC times C sub D divided by I. Here we are using delta maximum instead of delta sub XE. Delta sub XE, I have mentioned, is deflection typically at the center of mass of a level, except that it may be vertically aligned point below the center of mass of the upper level, or in the case of torsionally irregular building, C sub D could be at a point along the edge. Now, this delta sub capital M is maximum displacement at level X. This is maximum displacement, considering torsion and torsional amplification where applicable. So if it is a torsionally irregular building, you will have to consider the inherent torsion. You have to bring in accidental torsion, and depending upon your situation, you may have to multiply the sum of the two by torsional amplification factor. Okay, under all of that, the maximum deflection will be somewhere along the edge of the building, and that maximum deflection is capital delta sub M. So in other words, the delta sub XE typically does not include the effect of torsion. Delta sub capital M includes the effect of torsion. Is this page repeated? Seems to me. Yeah, I have two copies of the same slide, so you can just cross it out. Okay, structural separation. So that was what we discussed is the gap between two buildings on the same property. Now, where a structure adjoins a property line not common to a public way, property line not common to a public way, structure shall be set back from property line by at least the displacement delta sub M of that structure. So this is also a repeat. I don't know how it happened. Just cross out that slide. Okay, so previously we were talking about the shorter building and a taller building on the same property. But if there is a property line between the two buildings, this building belongs to one owner and the next building, the taller building, belongs to another owner, then the requirement is that this building must be set back by the delta sub M displacement at the roof, which is 75 millimeters in our case, from the property line. The adjoining building also has to be set back by the roof displacement, which would be, what did we say, 150 millimeters from the property line. And then the gap between the two would be 225 millimeters. So when the two buildings are on the same property, we are allowing a gap of 125 millimeters. When the buildings still adjoining belong to different owners, we insist on a gap of 225 millimeters. Is that logical? And the answer is yes, because if the two buildings belong to the same owner, our sole preoccupation is to avoid damaging contact. If the buildings belong to different owners, then what we are trying to prevent is from my building deflecting onto somebody else's property. Okay, so it is entirely what ASC 7 requires is entirely logical. Now, I had no idea so much time will go in this discussion. Anyway, time may become anyway, we'll see. So this is our beginning of our discussion of redundancy, or specifically the redundancy factor rho of ASC 7, which does not appear in BNBC any place. Okay, there is no rho factor in BNBC. In the design load combinations, it is assumed to be 1. So In SC7, I think it came up in discussion, there is a simplified design procedure, standalone section 1214. If you're doing simplified analysis, rho is equal to 1. Okay? That is something that I typically don't even think of mentioning. Now, if your design category is A, there is no seismic design, and what the rho value is immaterial. You don't have design category A in Bangladesh, so that goes out. B and C, very importantly, rho is equal to 1. D, E, and F, you don't have E and F. Design category D, rho can be 1 or 1.3. When we started out, rho was more complicated. Now it is design category D, E, or F. It is 1 or 1.3. The AC7 section on redundancy is 1234. In that, we first have a subsection that gives us conditions where rho can be taken equal to 1. Many situations AC7 tells us to start with rho can be taken equal to 1. And then the next subsection, we talk about redundancy factor for the high seismic design categories D, E, and F. Okay, starting with this slide, situations where rho can be taken equal to 1. AC7 tells us it can be taken equal to 1. Structures assigned to design category B or C. Drift calculation and P delta effect calculation. Okay, rho can be taken equal to 1. Drift computation and P delta effect calculation. Design of non-structural components, which we will discuss tomorrow. Rho is equal to 1. Design of non-building structures not similar to buildings. Non-building structures, again, we will discuss tomorrow. Very broadly speaking, every non-building structure is put into one of two categories. Non-building structures similar to buildings and non-building structures not similar to buildings. Non-building structures similar to buildings are treated like buildings, and the rho factor is whatever it is, but non-building structures not similar to buildings, rho can be taken equal to 1. Okay, that's item 4. Design of collector elements, splices, and their connections for which load combinations with overstrength factor are used. You remember this came up big time in the design of collectors. Their splices and connections must be designed using load combinations with overstrength factor. And when you have that overstrength factor included, you don't apply another rho factor on top of that. The rho is equal to 1. Design of members or connections where load combinations with overstrength are required for design. So it is not only the collectors, there are other things like columns supporting discontinued shear walls that have to be designed using the load combinations with overstrength factor. And if you are doing that, then there is no need for an additional rho. Diaphragm loads, diaphragm design forces that we will discuss later today. There are inertia forces that are generated in the diaphragm in an earthquake. And then there are transfer forces where we'll get into that. Rho for the inertia forces is equal to 1. For the transfer forces, it is what it is. It can be 1, can be 1.3. Structures with supplemental damping systems that are designed by chapter 18 of AC7. Rho can be taken equal to 1. And finally, design of structural walls for out-of-plane forces. So when you design a wall for out-of-plane bending, including the anchorage of that wall to diaphragms and so forth, rho is equal to 1. So this long list is extremely useful. We use it all the time. Okay, so going beyond that, if your design category is D, rho is 1 or 1.3. Okay, that I have said already, I don't know how many times. Now, rho is 1.3, not 1, 1.3, unless one of two conditions is met. Okay, if condition number 1 is met, then rho is equal to 1. If condition number 2 is met, then also rho is equal to 1. Both conditions don't have to be met. Okay, so unless you meet condition 1 or condition 2, your rho is equal to 1.3. This meeting of condition 1 or 2 doesn't have to be checked for the top stories of the building. You check, you do your check. So condition 1 and condition 2 only need to be checked at each story resisting more than 35% of the base shear. You do that check at each story resisting more than 35% of the base shear. Okay? So if you take this building, these are the story level forces, F4, F3, F2, F1 for the floor levels, 4 levels. The story shear in this story is that force. The story shear here is the sum of those two forces. The story shear at this level is the sum of all the forces above, and that is the base shear. Okay. Now, at this level, in level 4, the story shear is obviously no more than 35% of the base shear. So at the 4th level of this building, we do not have to check whether condition number 1 or condition number 2 is met. It is only in the lower stories that we will do that check. Now, condition number 1, condition number 2. What is condition number 1? Can an individual element, structural element, be removed from the seismic force resisting system? So can an individual element be removed from the seismic force resisting system without causing the remaining structure to suffer a reduction of story strength of larger than 33% or creating an extreme torsional irregularity? So you remove a member from the seismic force resisting system. If that causes more than a 33% decrease in story strength, the story from which you took that member, if the strength of that story goes down by more than 33%, or it now becomes extremely torsionally irregular, then you have not met condition number 1 and your rho is 1.3. So when we say you remove a member from the seismic force resisting system, what are these members? If you have a brace frame system, what you remove is a single brace. If you have a moment frame system, removal of a member would mean loss of moment resistance at the beam to column connections at both ends of a single beam. Okay, so you insert hinges at each end of a beam. These are not plastic hinges, these are hinges, zero moment. Okay, so that would be removal of a member when you have a moment frame system as your seismic force resisting system. When you have shear walls or wall piers, okay, so if you have shear walls as part of the resisting system, then you remove a shear wall with a height to length ratio greater than 1. That is important. You don't remove just any shear wall, but a shear wall with height, story height to length ratio greater than 1. And if it is a cantilever column system, it is you insert a hinge at the base of a cantilever column. Okay, so that's what we mean by removing a member. That is condition number 1. Condition number 2, if a structure is regular in plan, so all of this is condition. The structure has to be regular in plan. There are at least 2 bays of seismic force resisting perimeter framing on each side of the structure in each orthogonal direction at each story resisting more than 35% of the base shear. Too many each in this sentence, making it very difficult to understand. So I have a picture. So first of all, the first part was structure regular in plan. Okay, so there are no plan irregularities. That's what it means. You have 2 bays of seismic force resisting perimeter framing. Two bays in this direction, 2 bays in the orthogonal direction. So 2 bays of perimeter framing in each orthogonal direction, and the 2 bays will have to be 1 on each face, not in the middle. Okay, so it is exactly as shown in the picture. I'll read it now. It should be understandable. If a structure is regular in plan and there are at least 2 bays of seismic force resisting perimeter framing on each side of the structure in each orthogonal direction at each story resisting more than 35% of the base shear. So if you have this at every level other than the top levels where the story shear is less than 35% of the base shear, your rho is equal to 1. Okay, a few questions and answers which hopefully will make things clearer. Or the first item actually is an important part of the provisions. How many bays are there in a shear wall? So if when you have moment frames, it is very easy to count if you have 2 bays or not. When you have a shear walls, when you have a shear wall on a face, how many bays is that? So the number of bays is length of shear wall divided by story height. So if you have 10-foot story height, 20-foot long shear wall, your number of bays is 2. Okay, so length of shear wall divided by story height. But if you have light frame construction, I mentioned this is wooden studs, or these days cold form steel metal studs with some kind of sheathing. That would be light frame wall. If you have that, then you get a big break. Then the number of bays is twice the length of the wall divided by the story height. Does redundancy factor apply to the design of foundations? The answer is yes. I am using condition number 1, remember, removal of structural members, to determine rho for a wood frame building. All of the shear walls are relatively long. In other words, the height of each shear wall, 2.4 meters, is less than its length, which is 2.7 meters or 3 meters or 3.7 meters. Can I assign rho equal to 1 because there are no shear walls with height to length ratio larger than 1? And the answer is yes. ACE asks you to remove shear walls with height to length larger than 1. If there is nothing to remove, your building is redundant. We have a building that is 100 meters tall, 31 stories with shear walls. When table such and such uses the phrase height to length ratio, is that the height to length ratio within any story, or is it referring to the overall height to length ratio, which is for our building, which for our building would mean a height of 100 meters? The answer is the height to length ratio is intended to be story height to length ratio, story height, always story height. Okay, so as shown in this picture, when we talk about a shear wall with height to length ratio larger than 1, it is story height to the length of the shear wall. Can the value of rho be different for at different levels of the same building? The answer is no. The rho is for the whole building. Okay, it is not floor by floor. Answer is no. Rho cannot be different for different levels of the same building. However, depending on the structural system, rho can be different in the two orthogonal directions of the same building. If you are doing this element removal condition number 1, then you may very well find rho to be different in two orthogonal directions of a building. Okay, depending on the structural system, rho can be different in the two orthogonal directions of the same building if condition number 1 is used. Okay, if it is condition number 2, then even in the two orthogonal directions, rho cannot be different. Why doesn't table such and such address dual systems? If you have a dual system, can you assume rho is equal to 1? The answer is no. And AC 710 has commentary explaining why the answer is no. I in the interest of time, will not read the commentary. If you have any kind of an interest, I would strongly suggest that you read this slide and the next slide where the commentary ends. So for dual systems also, redundancy can be 1 or 1.3. You cannot just take it equal to 1. Dual systems are not listed in that front segment when I said rho can be taken equal to 1 for so many things. Okay, rigid versus flexible diaphragms. This is a very important topic because remember, we start seismic design with the design base shear. Then we do a vertical distribution of the base shear along the height, giving us the F sub x forces. From the F sub x forces, we can calculate story shears, V sub x. But then we have to make a horizontal distribution of V sub x. If in the direction of V sub x, as I showed you in a picture, if we have 2 frames and 3 shear walls of unequal length, or whatever we have, if we have multiple seismic force resisting elements, how is V sub x distributed among those elements? If we have 2 frames and 3 shear walls, how much of the story shear goes to the frames and how much to the 3 shear walls? How much goes to the frames and how much goes to the shear walls depend on the stiffness of the diaphragm. Does the diaphragm deflect very little in its own plane in an earthquake situation, in which case it is rigid? That will give us one kind of distribution. Or does the diaphragm deflect quite a bit in its own plane under design earthquake excitation, in which case our distribution will be very different. Okay, this is why we need to know whether our diaphragm is stiff or flexible. So Seismic story shear is to be distributed to vertical elements of the seismic force resisting system based on the relative lateral stiffnesses of those elements if you have rigid diaphragms. Seismic story shear is to be distributed to vertical elements of the seismic force resisting system based on tributary areas if you have flexible diaphragms. Okay? A very, very simple example. So we have a diaphragm, a slab bending in its own plane under the seismically induced forces. The stiffness of each shear wall is K. Stiffness would be the force required to impart a unit of interstory drift to those shear walls. Those are the same for all three shear walls. Okay. If the diaphragm is rigid, then 1/3 of this total force will go to each wall because the stiffnesses are the same. However, if the diaphragm is flexible, then half the total load will go to the interior wall and only a quarter will go to each of the exterior walls based on tributary areas. Okay, obviously this distribution is very different from that distribution. This is why we need to know the diaphragm rigidity, and these are two extremes. Obviously it can be something in between. The diaphragm can be semi-rigid. Most diaphragms actually are. We for purposes of analysis, we may take them to be rigid or flexible, but most diaphragms are semi-rigid, and we are now able to do structural analysis, including the actual stiffnesses of the diaphragms. That is called semi-rigid diaphragm analysis. It can be done, but it gets complicated. Okay, so next question is, when can we consider our diaphragm to be rigid? When can we consider it to be flexible for purposes of analysis? There is a prescriptive approach to answering that question. There is a calculation approach, both of which we will discuss. Okay. So when can a diaphragm be taken as prescriptively flexible? When can you assume a diaphragm to be flexible without any calculations? Okay. So the answer is diaphragms constructed of untopped steel decking or wood structural panels, if let me go to a picture and then maybe I'll come back to the text, maybe I won't. Okay, but this summarizes the whole provisions of ASC 7 when it comes to rigid versus flexible diaphragms. Okay, this picture is not in ASC 7. We put this together to explain the ASC 7 provisions. Okay. So if you want to figure out whether you can take your diaphragm as prescriptively flexible or prescriptively rigid, you will start here by asking, is my diaphragm made of wood structural panels or untopped steel decking? If the answer is yes, it is one or the other. My diaphragm is made of wood structural panels or untopped steel decking. Then the further question would be, is the diaphragm part of 1 and 2 family dwellings of light frame construction? You know light frame construction by now. If the answer is yes, then you can assume your diaphragm to be flexible. If the answer to that question is no, then you ask, is the structure of which this diaphragm is a part. Of light frame construction is the structure of light frame construction where conditions in section such and such are met. These two conditions are, maybe that's the only thing I will read. So you get to take your diaphragm as flexible if the structure featuring the diaphragm is of light frame construction where all of the following conditions are met. There are only two. It should have said both. Topping of concrete or similar material is not placed over wood structural panel diaphragms. No concrete topping, except for non-structural topping, no greater than 1.5 inches. Okay, there can be a non-structural topping. It will typically be lightweight something. Okay, so where both of the following conditions are met. So that is condition number one. Condition number two, each line of vertical elements of the seismic force resisting system complies with the allowable story drift ratio, story drift limits. Okay, so not just for the entire structure, but each line of lateral resistance shall meet the drift limits. If both of those conditions are met, then you can assume your diaphragm to be flexible. Thirdly, this is a big one. If your flexible if your diaphragm made of structural wood panels or on top steel decking is supported on rigid vertical seismic force resisting systems, which should be steel brace frames, composite steel and concrete brace frames, concrete masonry steel or composite shear walls. Those are all very stiff seismic force resisting systems. If the diaphragm itself is wood panel or on top metal deck and it is supported by very rigid seismic force resisting systems, then also you can assume your diaphragm to be flexible. If none of those conditions is satisfied, then we will go to the calculation approach. The prescriptive approach doesn't give us an answer. Okay. Now, if the answer to the starting question is my diaphragm made of wood structural panels or untopped steel decking, if the answer to that question is no, that means we have a concrete slab as our deck, as our diaphragm, or a concrete filled metal deck. So it's a metal deck with concrete topping. Those are the only two possibilities. If the diaphragm is not made of wood structural panels or on-top steel decking, because there is no masonry diaphragm. Okay? So concrete slab or concrete filled metal deck. If the answer is yes, we have one or the other, then you further ask, is the span to depth ratio smaller than or equal to 3? And is my diaphragm totally free of irregularities? Okay. Span to depth ratio less than 3 and no structural irregularities. If both of those conditions are satisfied, then our concrete diaphragm or concrete topped metal deck diaphragm can be considered to be rigid for purposes of analysis. Okay. If the answer to this question is no, or the answer to that question is no, then we have to go to the calculation approach. Okay. So this chart of prescriptively flexible diaphragms and prescriptively rigid diaphragms, I submit to you, is extremely, extremely important in the scheme of things. When you do design using ASC 7, this is something you will need to figure out. Okay, calculated deflection approach. Again, I will skip the text, go to the figure. You see my arrow. something pops up every few seconds and I have to get rid of that. Anyway, it's so annoying that. Okay, so this is a diaphragm. It is acted upon by seismic forces, inertia forces caused by seismic excitation. We typically take it uniformly distributed along the edge of the diaphragm. This is the in-plane deflection of the diaphragm, calculated value. And there are calculation procedures available depending upon the material of the diaphragm. Okay? So this MDD is the maximum diaphragm deflection calculated value. The loads applied along the edges of the diaphragm will go to the supporting seismic force resisting system if these are two shear walls. If the two shear walls are identical, half the load will go to this shear wall, half the load will go to that shear wall. Okay? If that shear wall is twice as stiff as that shear wall, 2/3 of the load will go to the stiff shear wall, 1/3 to the other shear wall. Anyway, we will calculate the interstory drift of this shear wall under its tributary load, and we will calculate the interstory drift of that shear wall under its tributary load. The average of those interstory drifts is ADVE. If the in-plane deflection of the diaphragm is more than twice the average interstory drift of the supporting seismic force resisting systems, then you have a flexible diaphragm, flexible by calculation. We do not say if the deflection is less than 2, you have a rigid diaphragm. ASCE 7 doesn't say that. Okay, so ASCE 7 has prescriptively flexible, prescriptively rigid, and flexible by calculation. Okay, this is now ASCE 7 requirement. The structural analysis shall consider the relative stiffnesses of diaphragms and the vertical elements of the seismic force resisting system. This is a requirement. Unless a diaphragm can be idealized as either flexible or rigid in accordance to section such and such, the structural analysis shall explicitly include consideration of the stiffness of the diaphragm, that is semi-rigid modeling assumption. So ASCE 7 is requiring it unless your diaphragm can be idealized as either flexible or rigid by the ASCE 7 provisions that we went over. Semi-rigid diaphragm analysis, as I said, can be done, but it is kind of complicated. So there is a lot of desire to get around it, and a way out is provided by the IBC. Okay, I went to 2015, 2018, 2021. Before that, 2012 and so forth. This was there, but it was in the definition section. There was a definition of a rigid diaphragm that says it is any diaphragm that is not flexible. So that went out after 2012 IBC, but let us read this. This is all important. A diaphragm is rigid for the purpose of distribution of story shear and torsional moment when the lateral deformation of the diaphragm is less than or equal to 2 times the average story drift. In other words, if a diaphragm is not flexible by calculation, it can be considered to be rigid, and that makes it unnecessary then to do semi-rigid diaphragm analysis. And I mentioned previously that the code controls over the standard. So you can legitimately say that since this provision is in the IBC, we do not have to go by this AC 710 requirement of semi-rigid diaphragm modeling. Okay, so that brings us to a good point for it's almost exactly 9:30. So we'll come back at 9:35 after a short break. Okay, thank you. Okay, I think it's time. So we will start on this segment. I titled it Basics of Structural Diaphragms, and then I'll talk about diaphragm design force level. I think on a previous occasion, I did talk about these technical briefs, as they're called, issued by the National Institute of Standards and Technology, NIST. A long time ago, it used to be called the National Bureau of Standards, NBS, back in those days. These are 40-page publications, roughly 40, on each on a highly technical topic. And the idea is to present to the practitioner a balanced overall view of the topic, how to deal with whatever is being covered in design. There is a tech brief on seismic design of cast-in-place concrete diaphragms, cords, and collectors. As you see here, it is tech brief number 3. I mentioned previously, you can Google and find it and download it totally free of charge. In this background section, I have taken quite a bit of material from this publication, particularly the figures. Okay, I did want to acknowledge it, and I also wanted you to refer to this publication as being almost must reading if you want to understand structural diaphragms. ACI 318 now has a whole chapter 12, relatively new, on essentially non-seismic design of diaphragms. Seismic design is in the seismic chapter 18, in one subsection. The provisions of chapter 12 of ACI 318 were largely derived from this publication. Okay, so this is something I did want to bring to your attention. This picture is lacking in quality, but anyway, it's isometric view of a basic building structural system comprising horizontal spanning elements, which are diaphragms, vertical spanning elements, which are walls and frames, and foundation. So the foundation is here. This is gravity. So the lateral force resisting system in one direction consists of this frame, and the other direction the shear wall. Everything else is gravity framing. You remember, those are structural elements that are considered not to be part of the seismic force resisting system. So the diaphragms are marked moment resisting frame, gravity frame, foundation, shear wall. Okay, this figure is about roles, multiple roles that diaphragms play. Diaphragms, again, I said this before, but I think it bears repeating. A slab, as you see here, we would, to get down to very basics, we would build the slab so that we can impose live loads on it, so that we can carry on some activities on the floor, whether the activity is sleeping or working or dancing or whatever. In order to impose the live loads, we will have to resist the dead loads, the weight of the slab primarily, and we will also have to, okay, let me pause there. So the dead loads and the live loads are gravity loads that cause out of plane bending of the slab. and a slab has to be designed for that out of plane bending. We have to put reinforcement in to carry the out of plane bending and the accompanying shear. When the building of which this slab is a part is subject to wind forces or forces due to earthquake excitation, now the same slab will bend in its own plane like a deep beam. And now we call the slab a diaphragm. Okay, the slab is acting as a diaphragm. And acting as a diaphragm, it fulfills multiple roles. Okay, so these are lateral loads, these are gravity loads, this is diaphragm, here moment resisting frame. In this picture there is an inclined column, there is a thrust on it. Anyway, so this is shear wall, gravity framing as in the previous picture. This is called a podium slab or a transfer slab, and I'll talk about that. And these are basement walls. Okay, this is below grade soil pressure. So this is a pretty general picture that that we encounter fairly commonly. These are the different roles that diaphragms play. This is gravity loads, not acting as diaphragm, acting as slab, but anyway, that's a role. Provide lateral support to vertical elements. That is important. Laterally, so diaphragms provide lateral supports to frames, shear walls, and so forth. Resist out of plane forces. I don't know any difference between the first item and the third item. This is NIST's list that I reproduced. Resist thrust from inclined columns. So that thrust, or this thrust, has to be resisted by force in the diaphragm. That is pretty uncommon, inclined columns. Transfer lateral inertia forces to vertical elements of the seismic force resisting system. This is huge. This is a major role that diaphragms play. Transfer lateral inertia forces to vertical elements of the seismic force resisting system. Also transfer forces through the diaphragm, and if you go all the way down, support soil loads below grade. Now, when we have shear walls and frames in the same building, shear wall frame interactive system, or it could be dual system, whatever, the frames left to themselves would deform as shown in the left picture. This is called the shear mode of deformation. The wall left to itself bends like a cantilever, flexural mode of deformation. When the two are tied together at every floor level through the diaphragms, neither can do its own thing. The diaphragms impose equal displacements on the frames and the shear walls at every floor level. In the process of doing so, there are forces induced in the diaphragm. Those are the transfer forces. Forces are transferred between the frame and the shear wall through the diaphragm, and in order to equalize the deflections of the frames and the shear walls. When you have this kind of a situation, at this level, the base shear from the upper portion, part of it will go to this seismic force resisting system. It will not all be resisted by just that. So there will be significant transfer through this slab, large diaphragm transfer. At the bottom, okay, there is huge story shear, huge base shear that will be resisted by the walls of the basement. But the shear has to go to the walls of the basement via the podium slab, and maybe there are other diaphragms below that are also transfer diaphragms. So floor slabs are very typical diaphragm elements. Floor slabs acting as diaphragms, very common. But it could be roof decking acting as diaphragms, not uncommon. It could be this we saw in Chile, uh, quite a bit actually in industrial buildings. The on this horizontal plane there is bracing, okay, bracing parallel to the floor on the horizontal plane, and that bracing acts as the diaphragm. So stiffness in horizontal plane can come from flexural stiffness of cord members or from bracing in a horizontal plane. Bracing in a horizontal plane was very popular in at least the parts of Chile that we visited. Cross bracing on the roof can also act like diaphragms. Now, when a diaphragm is subject to lateral loads due to wind or earthquakes, there would be, if this is the direction of the lateral load, there would be tension on this face, compression on the other face. The tension has to be taken by reinforcement. We have no choice. Concrete doesn't carry much tension. And the structural element or the part of the slab where we put this reinforcement is a tension cord. There is a tension cord. There is a compression cord also on the other side. The thing is that the compression cord will be reinforced exactly the same way as the tension cord, because when the earthquake direction reverses, this will be the tension cord and that will be the compression cord. Okay. Along the edges of the diaphragm, there are shear stresses. Obviously, this is a beam bending in its own plane. So there is bending causing tension, compression, and then there is shear. The shear will be transferred to the shear wall. That is in the next picture. The variation of shear force across or the variation of shear force from here to there in the diaphragm is shown in the picture, and the variation of bending moment in the diaphragm is shown in this picture. Okay, I think this is a simple picture that doesn't require much of an explanation. Now, the shear, if the entire diaphragm edge were supported on a shear wall, it would have been direct shear transfer. The diaphragm edge shear would be transferred to the shear wall, and that's it. However, in this case, we have 60 feet of diaphragm edge, 20 feet of shear wall. Okay, so the shears over the 20 feet have to be collected and delivered to the shear wall. So the shears build into a compression force that is transferred to the shear wall, and then this side we have a high those reinforcing bars are in compression, and on this side they're in tension. The the direction of the arrows and everything will tell you that those bars are in tension. The tension is the highest at the junction with the shear wall, and then it goes down to zero by the time you have arrived at the end of the diaphragm. Okay, so those elements are called collector elements or drag struts. They collect the shear force and delivers it to the resisting shear wall. Collector element. Okay, so we have to put reinforcing bars to carry the tension. The same reinforcing bars will be here because if the earthquake direction reverses, that portion of the collector will be in tension. And the other part of the picture is showing us that sometimes, because of construction reasons, we would spread out the collector element, the collector reinforcement. But there are limitations to how far you can go. The structural engineers of Northern California have some recommendations that are, I think, pretty sensible. Now, when a shear wall, or this could be a whole tower, sits on a podium, which is very, very common. Okay, a tower, but then very low levels. We have a much bigger structure. Okay. So the base shear from the tower or the shear wall will ultimately be resisted by those basement walls. But how do you go from here to there? And this is like the collector. Okay, so the the base shear will cause shear stresses in the diaphragm. So shear stresses in the diaphragm, you can imagine the shear stresses, and the shear stresses build up to tension in this part, and it is large compression here and then decreases to zero. This is the opposite of the collector, many times called the distributor, but the same principle. These reinforcing bars are absolutely needed to take the base shear into the diaphragm, and then from the diaphragm it goes to the basement walls where they are resisted. Key points on diaphragms. Diaphragms are horizontal elements that transfer lateral forces to lateral force resisting elements. Diaphragms can be floor or roof slab or could be bracing. Diaphragms are classified depending on whether they are flexible or rigid compared to the lateral force resisting system. We have talked about that. Exact and approximate analysis methods are available for each assumption, meaning whether you assume flexible diaphragm or rigid diaphragm. And then diaphragms can be designed as deep beams and detailed to resist flexural tension, shear, and it could even be direct tension. Now, if diaphragms are flexible, flexible diaphragms typically are, take the parking structure. A parking structure bay is about 60 feet wide. That doesn't vary, could be 62 feet, but something in that range. In the other direction, you go these days 300 feet maybe. Not always 300 feet, but you can go up to 300 feet or more. So that gives you a diaphragm aspect ratio of pipe 300 by 60. And that is a very flexible diaphragm. The span is long, 300 feet, and the span to depth ratio is large. 5 is very, very large. Below 3 is kind of not very flexible. Okay. So that kind of a diaphragm, flexible diaphragm, essentially takes over the dynamic response of the structure. I Well, I may have gone a little too far when I said that that depends upon the building. That can happen. That doesn't happen as a matter of course. But anyway, what does happen? Okay, let's look at this. Uh, when the diaphragms are very flexible, they would increase the fundamental period of vibration of the building. Remember, we calculate the period of vibration as height raised to the power something, considering only the vertical elements of the seismic force resisting shear walls. If it is a frame building, it is a coefficient times height raised to the power something. If it is a shear wall building, it is another coefficient times height raised to the power something else. But the diaphragm, if it is flexible, will increase that period. And as the period increases, initial period may have been, so this is the design spectrum. Initial period may have been here. So this is our design force. The elongated period may be here. The design force has come down very significantly. That can happen when the diaphragm is flexible. Now, whether the forces will decrease or increase or what will depend upon the spectrum, the response spectrum of the earthquake that is hitting our structure. But the point is that the period is changing. Also decouple vibration response of vertical and lateral force resisting systems. Let me show you the next picture. Modify distribution of lateral force to lateral force resisting elements. All of these things can happen. Decouple vibrational response of vertical and lateral force resisting systems. Modify distribution of lateral forces to lateral force resisting elements. We have talked about that. If the diaphragm is rigid, it's one distribution. If it is flexible, it is another distribution. The decoupling. So this is the direction of earthquake. Parallel walls act as shear walls. The perpendicular walls, they are bending out of plane. Perpendicular walls respond out of plane to excitations of the floor slab and the roof diaphragm. So the wall is vibrating out of plane, and the diaphragm is doing its own thing in its own plane. Okay, and unless the connections between the walls bending out of plane and the diaphragm are very strong, there is even possibility of the diaphragm separating and causing serious problems. That has happened innumerable times. Okay, so anyway, the point here is that the out of plane vibration of the wall and the in-plane vibration of the diaphragm are not in consonance. They do not move together. Okay, so the outer plane wall is doing that, and the diaphragm, if the base acceleration follows this history, the diaphragm displacements will probably look like that. We have looked at something like this when we introduced the concept of the response spectrum. Okay, so the diaphragm is deforming in its own plane following this history. What the wall bending out of plane doing is not exactly the same thing. This is the decoupling that we are talking about. Okay, design of diaphragms, the web of the diaphragm is designed to resist shear, and the bending is resisted by the tension compression cords. The tension force in the tension cord and the compression force in the compression cord, the couple between the two, resist the moment. So resist fractional tension using cord elements, which consists of reinforcing bars typically, but you can have physically enlarged sections like beams acting as collectors or cords. Resist shear using web, provide collector elements or drag struts to resist direct tension in slab, as mentioned previously. Okay, so if the diaphragm edge is 40 feet, the shear wall length is 20 feet, this would be a collector element that would require tension reinforcement. For one direction of earthquake, that element will be in tension. For the other direction of the earthquake, it will be in compression. Okay, so those are the basics. Now we come to diaphragm seismic design force level, which has been a pretty hot topic in recent years. So I go to AC 710, 1210.1, AC 705, it was also 1210.1, very, very important section on diaphragm design. This is where you come for the design of your diaphragm. And diaphragm has to be designed. I told you to start with BNBC does not have these provisions. All it says is the two-page thing two-slide text that I showed you, but diaphragms need to be designed, particularly seismic design category D. Okay, so diaphragm shall be designed for both the shear and bending stresses resulting from design forces. Add diaphragm discontinuities, that part you can read. I don't know that. I can. Okay, now you have to follow me closely here. This is very important stuff. Okay, so the beginning again is the design base shear V. We calculate it and then we distribute it along the height of the structure in the manner prescribed by the code. Linear variation, 0 at the base to a maximum at the top for buildings with period less than half a second. Parabolic distribution for buildings with period more than 2.5 seconds. In between, we do an interpolation between a linear and a parabolic distribution. That gives us the F sub I forces, F sub I at floor level I. Okay, that distribution is shown in red in the picture. Okay, this is a 1, 2, 3, 4, 5 level building. At the top level, you see the force. Next level, it is lower. Next level, it is lower, and so forth. Now the diaphragm at floor level X is not designed for the force F sub X. It is designed for a force equal to F sub Px. Again, very important. The diaphragm at floor level X is not designed for F sub X. It is designed for a diaphragm design force equal to F sub Px, given by this formula, where W sub Px is weight tributary to the diaphragm. Okay, Now, when you apply that formula, the diaphragm design forces at the various floor levels came out to what you see in blue. At the very top, there is no difference between F sub x and F sub px. That should be obvious from the expression. One level down, F sub px is larger than F sub x, and that is true of every level below. Okay, diaphragms are much more susceptible to higher mode effects. And those effects will impose higher forces on the diaphragms. Anyway, so that formula we have used for a long time, and that gives you the diaphragm design force distribution as shown in the picture. I will do an example here. I didn't try to change the units in view of comments made on earlier occasions. I think most of you are at home with the American unit, so I left it the way we had it. Okay? So a building with frames and shear walls, the shear walls are here. 1, 2, 3, 4, and one here. Okay. 30 foot, 20 feet, 30 feet bay. And this way, these are all 25 feet bays. The shear wall length is 30 feet. Same here. Okay, these are the seismic weights at the various floor levels. Seismic weight is something defined. I would not repeat or go into that, but make sure that this is the seismic weight, not just the dead loads at the various floor levels. Those are the heights of the various floors above the base. The first one is at 14 feet, the next one 28 feet, 42, 56. So the story height is 14 feet, which is a little unusually tall. This is W sub x times h sub x raised to the power k. K, remember, is 1 for stiffer buildings, 2 for flexible buildings, in between 1 and 2 for in between buildings. Okay. So this is the summation of W sub x, h sub x, and the lateral force at level x is this divided by the sum multiplied by the design base shear, and those forces at the various floor levels came out for our building to 163 kips at the top, 145 next level, 115, 86, 57, 28. Okay. So this is standard calculation, distribution of the design base shear along the height of the structure. I should have mentioned and didn't somehow that this force F sub px has an upper bound on it beyond which you need not go. If you go above, no penalty, but you need not. And the upper bound is 40% S sub ds, the short period design spectral acceleration, importance factor, and again weight tributary to diaphragm at level x. The diaphragm design force also has a lower bound on it below which you shall not go. The lower bound is mandatory, the upper bound is up to you. The lower bound is 20% of S sub ds times I times W. So in our case, the upper bound 40% S sub ds IW is 40%, S sub ds apparently is 0.34, I is 1, W sub px from the table is 1962 at a typical level, and that gives you 267 kips. The lower bound of 20% S sub ds is one half of that, that is 133 kips. Okay, now we calculate the diaphragm design forces from this formula. These are W sub px, the weights tributary to the various flow levels, the F sub x, the lateral forces that we obtained by distributing the design base shear. Those are some of these forces as you go down. This 308 is 163 plus 145. These are the summations of the weights. The 3787 is 1825 plus 1962. And with this and that, we are able to calculate the F sub px, the diaphragm design force at level x. At the very top, it is the same 163, which is the lateral force. But at every level below, it is higher than the lateral force. Okay. Now, at these levels, we go below the minimum 0.2 S sub ds IW, so the minimum will govern. We will use the minimum values in design. Okay. So these are the F sub x forces resulting from distribution of the design base shear along the height. These are the diaphragm design forces. I want you to see this. This is not very different from where we started. The diaphragm design forces in blue and the lateral forces at various floor levels in this red or whatever that color is. Okay, so you are looking at the same picture here, and you will always get this picture. So diaphragms have to be designed for higher forces than the F sub x forces. Actually, the AC7 says you can never go below F sub x with your diaphragm design force level. Okay, collector elements. I used this picture in one of the earlier segments, and I have mentioned this already. So this is the diaphragm. These are the lateral forces. If this is the direction of the lateral forces, this edge of the diaphragm will be in tension, that will be in compression, and there will be shear forces along the diaphragm edges. If the entire diaphragm edge were supported on a shear wall, it would have been a direct shear transfer, but it is not. We have so much of diaphragm edge, only so much of shear wall. So something, at least a bunch of reinforcing bars, has to collect the shears into a compression force that has to be delivered to the shear wall. When the earthquake direction reverses, it will be the same reinforcing bars will be in tension. Okay, you can visualize that. Okay, and we have to reinforce the collector for the tension. The compression is not a non-problem to, I mean, we cannot just disregard the compression saying that concrete is strong in compression. Yes, concrete is strong in compression, but if the compression becomes high beyond a certain threshold, concrete needs to be confined. So there are provisions in ACI 318 that requires us to very tightly confine the collector element, okay, particularly at splices and so forth. So you have to be mindful of the compression as well. It is not just the tension. Anyway, this slide makes the point that the same, okay, so for this direction of seismic forces, this is the tension cord, this is the compression cord, and the collectors are here. Okay, so for this direction of seismic forces, this is the compression cord, this is the tension cord, and those are the collectors. For this direction of earthquake forces from left to right, okay, those are now the collectors. The elements that were cords for the perpendicular earthquake direction are now serving as collectors, and the elements that were collectors before will now serve as cords. So this happens. These are interchangeable roles. Okay, a cord can serve as the collector may serve as the cord. Okay, where the diaphragm is required to, okay, so this is the other thing that I think is important. So inertia forces develop in the diaphragm. Okay, this we have talked about at much length over probably 2 or 3 different lectures. But then if the seismic force resisting shear walls makes an offset like this, the shear wall comes down on your slab. Instead of continuing straight down, it makes a bend and then comes down. The shear at the end of the shear wall will have to go to the top of the continuing shear wall through this floor slab. So the shear will be transferred from the upper wall to the lower wall through this portion of slab. That will mean there will be high transfer forces in that slab. That transfer force has to be obviously considered in the design of that portion of the diaphragm. Okay, so where the diaphragm is required to transfer design seismic force from the vertical resisting elements above the diaphragm to other vertical resisting elements below the diaphragm due to offsets in the placement of the elements or to changes in relative lateral stiffness in the vertical elements, these forces shall be added to the inertia forces. I mentioned to you already, when it comes to the inertia forces, redundancy factor is equal to 1. When you design your diaphragm, your redundancy factor is 1. However, on the transfer forces, the redundancy factor is 1 or 1.3, whatever you have calculated for your structure. If you have calculated a rho of 1.3, you have to apply that rho on the transfer forces. You don't apply, remember, rho is in the designed load combinations. When you are combining the effects of earthquake forces with the effects of gravity. Okay, so this transfer force will be an earthquake effect. If the lateral forces you are transferring are seismic forces, then the earthquake effect will include the rho factor, and the earthquake effect will then be combined with the gravity load effect through the load combinations. Okay, so it is not that you multiply the transfer force by rho. No, you find the effect of the transfer force, whatever it is doing to the diaphragm. Those will have to be amplified by rho and then added to the effects of inertia and so on and so forth. Now, this is a picture of what actually happens. This multi-story building was tested on the outdoor shake table at University of California, San Diego. Some earthquake motion was imparted to the shake table, and the accelerations of the various floors were measured. And you are looking at the measured accelerations at the various floor levels. So this is the acceleration of the ground or the shake table. This is acceleration of floor level 1. 2 is not in the picture. Floor level 3 acceleration, floor level 5 acceleration, floor level 7 is the top level. You see that the floor acceleration goes up as you go up the building. This is pretty typical. At the roof level, you will typically experience 2 to 3 times the acceleration at the ground level. Okay, 3 times is not all that terribly unusual. So that means that the roof diaphragm needs to be designed for much larger forces than the lower level diaphragms. Okay, are you with me? So this is something ASCE7 did not recognize until something happened in the 2016 edition that I will mention to you. So this is a picture where we have shake table test data and data that were gathered from actual buildings after the Northridge earthquake. On the x-axis is peak ground acceleration. On the y-axis is floor magnification, meaning the floor acceleration is twice the ground acceleration. Floor acceleration is 3 times the ground acceleration, and so forth. Okay. So these are the measured points. Floor magnification, actual observed floor magnification, observed or measured in shake table test as a function of peak ground acceleration. This is the ASCE7 upper mount diaphragm design force. 0.4 S sub ds I times W. This is the lower mount ASCE7 diaphragm design force. We need not ever exceed 40% S sub ds times I times W. And you see that that maximum is lower than all the points from measurement as well as observation. So that tells you that we are under designing our diaphragms. The diaphragm design force is very likely going to be much larger than what you are designing for. So based on these observations from many sources, in PCI's seismic design manual that Ned Cleland and I put together many years ago, we made some recommendations for structures assigned to design category D, E, or F. If lateral forces are resisted entirely by special moment frames, additional load factors are not required, if every floor diaphragm is designed for the force at the uppermost level. So design category D, entire seismic force resisting system consists of special moment frames. You design all the diaphragms for the roof level diaphragm design force. You don't go down the height of the building. You design all the diaphragms in the building for the roof level diaphragm design force. Our recommendations were picked up in the PCI design handbook, and part of the recommendation is for structures assigned to design category D, if shear walls are part of the lateral force resisting system, it is sufficient to apply a diaphragm load factor of 2 to the force at the uppermost level and to design each floor for that force. So now you design the roof level diaphragm for twice the force level you calculate from ASC 7, and then keep it constant down the height of the building. Don't decrease it any further. This was our recommendation. Lately, and this may be my last slide, maybe there is another, I don't remember. No, this is it. Yeah, okay. Lately, there has been quite a bit of development in this regard. This was led by an issue team, though those details may be not important to you, but the development took place within the 2015 NARP provisions that I'm sure I mentioned to you earlier. These days, part one of the NARP, so first of all, 2015 NARP provisions adopted ASC 710 and then made a small number of modifications in part one to the provisions of ASC 710. One of those modifications was a different diaphragm force level. We retained section 1210.1 as it is. Everything that I showed you is still in ASC 7, but then there is an alternative diaphragm design force level in section 12.10.3 of ASC 7, which originated in the 2015 NARP provisions. This alternative design force level is mandatory for precast diaphragms in design categories C and D. It is allowed to be used, not required to be used, for design category B precast diaphragms, cast in place concrete diaphragms, and wood diaphragms supported on wood framing. Steel deck diaphragms are not included in that list. Steel industry felt more research had to be done before they would agree to the different force level. So, new provisions were added to part one of the 2015 NARP provisions. These provisions, with a small number of modifications, became part of ASC 716, that is section 12.10.3 of ASC 716. Adopted is a design force level equal to the force that would keep the diaphragm elastic in the design earthquake, reduced by a diaphragm design force reduction factor R sub S that we came up with. This was a lot of work, and if you are interested, go to section 12.10.3 of ASC 716. We have added a very extensive commentary to explain how things came about, and that is how should I say, to reconcile this problem that observed force levels are high, our diaphragm design force levels are low, and we in this approach, the new design force level, we are essentially saying that uh, it's not as bad as it looks like. You don't have to design for the you do not have to design for the force level that will keep your diaphragm elastic in the design earthquake, because there is overstrength in your diaphragm, there is ductility in your diaphragm. With both of those being present, if you design for lower design force level, your diaphragm performance should be fine, and that's where the R sub S factor comes in. So that is a very significant development that I will not go into, because ASC 716 is a long way from ASC 705, which is the basis of your BNBC provisions. So I will end it here. Obviously, if you have an interest, then that is a very, very good place to go to. Thank you very much, and I am open to questions now.
Thank you, Dr. Ghosh. Yeah, so we have a lot of questions. I answered a few of them. Okay, so one thing that one of them pointed out is that today you referred to AC 710 instead of AC 705.
Yes.
Was there any particular reason?
I stated the reason. The building separation requirements that I shared with you are in AC 710. They were not in AC 705. So for building separation, I definitely switched. For the other portions, it does not make any difference whether it is AC 705 or 10, because things didn't change. That is true of the redundancy provisions. So it is not that I switched to AC 710 across the board, but for the building separation provisions, I definitely switched to AC 710.
Okay.
Diaphragm design force, AC 710 and AC 705 are the same if you are looking at section 12.10.1. So it doesn't matter whether I say 10 or 5.
So now that I'm going through the questions, I see there is a lot of confusion between like the collectors in a diaphragm and beams. Like, can beams
So
be
that again, confusion between what?
the collectors in a diaphragm, the collector elements in a diaphragm, and beams. So they are getting confused if beams can be used as collectors or not.
Absolutely. Quite often, yeah, quite often collectors are beams, but they don't have to be beams. They can be just a bunch of reinforcing bars that are entirely within the slab. I do not know why that would cause confusion. This is like shear wall boundary elements. That does not require a thickened shear wall end. You can have a rectangular wall with boundary elements, specially confined boundary elements detailed within that the thickness of the wall. It is the same thing. You can have beams which are fine. They will act as collectors. If you don't have beams physically sticking below your slab, you can have just a bunch of reinforcing bars acting as collectors. Both ways is totally fine, and both are very common.
Okay, so I think that answers at least 4 or 5 of your questions.
Okay.
In a beam column, is it required to design core? Yeah, this also you have covered. Can we consider slab on grade as a diaphragm if collector elements are inserted between slab on grade and column, but no connection between grade beams and slab on grade?
Read that one more time.
Can we consider slab on grade as a diaphragm if collector elements are inserted between slab on grade and column, but there is no connection between grade beams and slab on grade?
Yeah. The answer to the first part is yes. The slab on grade can be a diaphragm if you choose to take lateral forces through the slab on grade. Okay, does that require uh, collector elements? I, I do not see that. The I think the column shear will go through the slab without your inserting collectors, and why you cannot have connection with the grade beams, that again is not clear to me. Uh, yeah, the second and the third part of your question is not clear, but a slab on grade can be, and it is required to be designed as a diaphragm if you transfer lateral forces through it. The lateral forces may be from columns, maybe from shear walls. If it is lateral force from shear wall, then you will need some kind of collector elements or something to spread the load around. From columns, I don't think so.
Okay, Dr. Gus. When we separate two structures, what elements do we use to integrate them? I do not mean structure integration, but architectural.
I, anyway, there are a couple of things that I think are important. You cannot have anything that will uh, what do I want to say? The structures will need to deflect freely uh, with whatever you have installed in place. Yeah. So the gap has to be maintained. You cannot let it be filled with debris or whatever over the years, because then you don't have a separation. That is a necessity. If the outside, from the outside, you want to create the impression there is no gap, you can put something like plasterboard or something that will easily crumble in an earthquake, not uh, not interfering with the deflections of the two parts. So yeah, I think you get the idea. So you can put something to cover it up, but that something cannot be in the way when the buildings want to deflect. It needs to break pretty easily.
So, how to design podium slab to resist huge lateral loads?
They are sometimes feet thick. Feet. If it is a tall tower sitting on a podium, you can have 5 foot thick slab acting as the transfer diaphragm. So the design is no different from that of other slabs, but they can be, you have a lot of shear in the diaphragm, and that has to be, even with reinforcement, you need a lot of thickness.
So, there is one question referring to a previous lecture. You have calculated live load reduction factor based on IBC 2009. R is equal to 0.08 times some area, where area is in square foot. The alternative approach for live load reduction factor is not available in BNBC 2020. Can we still use that IBC? 2009 equation for reduction of live load?
You know, that is not for me to answer. You have to ask Rajuk or somebody. And I do not know. Since it used to be in all US codes. There is nothing wrong with it. So if you ask me, I think it is okay to use. But then you will have to deal with, your plan checker. And so I cannot take his place and tell you for sure.
Okay, doctors. To design a diaphragm, you mentioned only shear walls, but for columns, does the design procedures differ, or it is same?
It's just a diaphragm typically on sit on columns. It will sit on frames. Okay, and the shear transfer will be the same. It will go to the beams of the frame.
Okay.
Okay, and if it is high seismic, you cannot have flat plates as part of the resisting system. I told you. So you will not have a slab sitting on columns. Uh, how should I say? Flat plate columns will not be part of the resisting system. So you will never have a situation where your slab will not sit on a beam or a shear wall.
Yeah, that's a good answer. Um, so today you showed us how to calculate the diaphragm design force. Can you provide us with a design example by which we'll be able to use this design force for designing slabs?
I'll have to look. Ready-made diaphragm design examples are not very common. I'll have to look. Yeah, it will be good to have one.
Should I continue, Dr. Ghose?
Yeah, please.
Yeah. Okay, so this is a big question. So in a dual frame structure, most of the stories are extremely torsional irregular, and seismic force resisting system consists of more than two bays of moment resisting perimeter framing on each side of the structure, and in each orthogonal direction at each story, resisting more than 35% of the base shear. Can we still take the redundancy factor as 1.3 or 1?
Can you read the beginning?
In a dual frame structure, most of the stories are extremely torsional irregular. So they have extreme torsional irregularity in a dual frame building.
So the very beginning of what I presented, why is this master slide coming?
Can you can click on close master view? Do you see it? There's a big cross. Uh,
Big box where? Oh,
right. Yeah. Yeah.
you see the first line, if a structure is regular in plan, and there are at least two bays, etc. So if you have extreme torsional irregularity, you cannot use this approach. You have to go by removal of elements. It's very straight cut.
Yes. Mm, just a second. Any special detailing that is required to transfer lateral load to the shear wall through diaphragms for slabs for both rigid and semi-rigid diaphragms? You went over it, right?
Read that again.
Any special detailing that is required to transfer lateral load to the shear wall through diaphragm for rigid and semi-rigid diaphragms.
Mm. There are no detailing rules like we have for beams and columns, but obviously all the tension has to be carried by reinforcement, and if the compression is high, you have to be mindful of the fact that your concrete needs to be confined. So those are about there are some detailing requirements for the collectors, but the diaphragm, there is no detailing requirement as such. So you have to design for the shear, you have to design for the bending, and no, there is no how should I say, the basics still apply. If you have high compression, you will have to confine. Other than that, there is no particular detailing requirement.
Okay. And we use horizontal bracing systems as diaphragm.
Yeah.
That you mentioned in one of the slides. And then
I should. Yeah, if you can imagine on this horizontal plane into the screen, horizontal bracing, that would be that would serve quite well as diaphragm. Yeah, this as I said, we saw in I think it was in and around Santiago, Chile. The industrial buildings were many of them that way. That was their diaphragm.
yeah, this question is not clear. I will just tell him to clear this question once. Like clarify. Do you provide all question and answer session for all sessions? We do at the end.
What was the question?
That do you have question and answer sessions after at the end of all question and answer all sessions
Yeah,
basically?
I think there was one day there was an exception. I went up to 11.
Yeah, sometimes the content is that much that there is no time
Yeah,
left.
but it happened only once, I think.
Yeah, but most of the sessions we do have.
Yeah.
Um, so we will appreciate if you can discuss the difference between or relation between drift and displacement.
It's very, very simple. I have discussed it many times. Deflection is deflection, okay? If you are talking about floors under lateral load, how much does the floor move sideways? That is deflection or displacement. The drift is interstory displacement. Drift is deflection at the top of a story minus the deflection at the bottom of the same story. That's very, very important, okay? Deflection is for a floor level, drift is for a story. And drift is deflection at the top of a story minus the deflection at the bottom of the same story. And then the drift can be elastic drift. That would be the elastically computed deflection at the top of the story minus the elastically computed deflection at the bottom of the story. Or it can be what we call design drift, which will be the elastically computed displacement at the top of the story minus the elastically computed deflection at the bottom of the story, the whole thing multiplied by C sub D, the deflection amplification factor, and depending upon what you are doing may be divided by the importance factor I. Now, if this drift, the design story drift as it is called, is divided by the story height, that is called the design story drift ratio. But the difference between deflection and drift is as simple as that. As simple as I said, the deflection is for a particular flow level, how much it moves sideways under lateral load. And the drift is for a story, and that is the deflection at the top of the story minus the deflection at the bottom of the same story.
Okay, Dr. Ghosh. So while calculating soft story effect, should we account for the stiffness of the story below grade beam, that is basement or surrounded by soil?
There is nothing called soft story effect that I know about. You deal with soft story the way it is. It is a stiffness discontinuity by definition. Quite often, soft story goes together with weak story. There is also a strength discontinuity. Whether you consider whatever lies below, it depends on where your base is. Base is defined in AC7, and I'm sure it's in BNBC, as where earthquake ground motion is assumed to be imparted to the structure. It is up to the engineer to decide that. Okay, so if your base is, let's say, at the ground level, whatever, the top of the basement, then there is no reason for you to consider the rest of it. You go from the base up. I hope I answered the question.
Yeah, that was a very good answer. So in commercial design software, the shear wall force is used in some load combination in just top of the base and requires a lot of rebar. What would be the remedy? Or do you think it is correct?
Read that again.
In commercial design software, the
Mm.
shear wall force is used in some load combinations just at the top of the base and requires a lot of rebar. Do you think this is correct, or is there any remedy for it?
I have no reason to believe it is incorrect. I mentioned again many times, even when you have shear walls and frames in the same building, near the very bottom of the building, almost the entire story shear goes to the shear walls and nothing to the frames, or very little to the frames. This is why in a dual system we do the second analysis with the frames carrying 25% of the lateral forces. Otherwise, you will be designing very weak columns. So the shear in the shear wall is typically quite high in the lower portions of the building. They do require a lot of reinforcement, and there is absolutely nothing wrong with that. At least I do not see anything wrong. It is not the problem of software. It is that's the way buildings behave.
Okay, so one of them is asking that we needed reinforcement detailing for diaphragms.
There is no in response to a previous question, I answered that we don't have that. We don't have a set of detailing as we do for shear walls. Okay. You, I don't know what else to say.
Same question again. So I will say this is
Look,
replied.
look at the ACI 318 has a whole section on diaphragm in part of chapter 18. It's 1811 or 1812, I don't know, something like that. So it is the section on diaphragms. Look in there and see what you find. Everything that is said by ACI 318 on detailing of shear walls is in that section.
Okay. So there was one question that I asked for clarification. So he clarified. Do the diaphragm forces need to be resisted by concrete shear capacity only? Because Dr. Ghosh mentioned that podium slabs are sometimes some feet in thickness.
What's the question?
Do the diaphragm forces need to be resisted? Let me rephrase it. So, are the diaphragm forces resisted by concrete shear capacity only? Because, yeah, as you mentioned that the podium slabs are some feet in thickness. So,
Yeah, well, even if you have a reinforcement, that no, the answer to the question is it doesn't have to be carried by the concrete only, but uh, first of all, are you in a position to provide what do I want to say? If you I let me think for a second. I think the best answer I can give you is even if you provide shear reinforcement, you will still need a thick mat, thick podium slab. 5 feet may be an exaggeration that you find very seldom. 5 feet, but 2 feet, 24 inches, 30 inches podium slabs are not at all uncommon, and we need that even when we have reinforcement carrying part of the shear. Shears are very high. It's several thousand kips at the bottom of those towers, and that all has to go through the slab. So the answer, basic answer to your question, no. We don't have to rely only on concrete to carry shear. If we are prepared to provide reinforcement, that's fine. That's allowed.
um, so let me just. This was already answered in the question and answer before, so I don't want to go over it again. This question is not clear at all.
Hmm.
Is there any code provision to check overall deflection of the structure?
What does it mean? Overall deflection. So under wind in BNBC, there is a limitation on overall deflection. Under seismic, we have limitations on interstory drift. no check on overall. Never has been. But interstory drift, as discussed many times by now, have to be within tolerable limits.
The extreme torsional irregularity question, that Dr. Ghosh went over in length today, and I believe like this question was asked before. I think you might not have heard it before, so just go over the recording once. He has answered this question. Dr. Ghosh, most of the questions, relevant questions, you have answered already.
Okay.
And it's already 11 o'clock. So,
Okay.
yeah, let's end the session today. I think most of the questions you have answered, and the other
Okay.
questions are not clear or they have been answered already in some way. So,
Okay.
yeah.
Thank you.
Thank you, Dr. Ghosh, and we'll see you tomorrow for the last seismic session, I guess.
Yeah.
And
Yeah.
yeah, and thanks again for joining in huge numbers. And please provide your feedback, and I will turn on the quiz in a couple of minutes. Thank you so much.
Thank you.